For this project, I am making a MHD reaction wheel. I have it right here. Its mechanism is based off of the Lorentz body force that is imparted on a conductor when it experiences orthogonal magnetic and electric fields. In this case, it's an axial magnetic field and a radial electric field. The motion inside of the channel takes a lot of equations to actually model it, but we can probably get away as a first approximation with just F equals J cross B. And the magnetic field strength inside here, which is like B, is pretty much constant. I'm using permanent magnets, and they are surprisingly strong. I had an initial estimate of holding force of about 7 pounds, but when it's actually assembled, it feels a lot greater, which is good. It means that I should have a greater force per unit amperage or current, and that is what I want to maximize. I want as much current flowing through here as possible. It has a pretty low resistance, on the order of like 1 ohm. I have to make a power supply. I only got the manufactured parts of this on Friday, so I spent a few hours gluing the magnets in, and they are not happy about being packed in this arrangement. It took quite a lot of force to get each one into its place, but it turned out well. It's 40 magnets in, I guess, 20 pairs, if you can really call it that, and I only had a mishap on one. It had quite the opposing force, so I had to kind of squish it in there with a pair of pliers, and it put a small crack in the casing, but it shouldn't really cause any issues. There shouldn't be any leaks. What's next for this is the power supply, the control system, and a heater. I couldn't use a metal that was a liquid at room temperature since you can't get mercury in Canada, and I was quoted very high prices for gallon stand, which is what everyone else, it seems, has used. So instead I went with just like pure gallium, and it melts at about body temperature, but it does need heating. Gallium also super cools, so it only needs a heater at first in order to melt it. After it's melted, it remains a liquid for a pretty wide temperature range. After I make a power supply and a heater for this, what's next is performance capture and evaluation. I'm planning on attaching a MEMS accelerometer or gyroscope somewhere on the assembly, and we'll use that to capture the performance characteristics. I also need an air bearing or a table, so I'm going to ask Professor Ulrich if I can use his. And that's pretty much where we're at. While it was open, I did apply a voltage across the electrodes, and it did move, so it does work. Only challenge now is to actually quantify how well it works, and that's what's next.